Good morning, good afternoon, good evening, everybody, wherever you are in the world, and welcome to EMinar Wednesday. It gives me great pleasure to get a talk today from Christine Chesley on, well, we'll talk a little bit more about Christine's talk in a minute. But before I do, just to remind you, those of you perhaps new to these EMinars, are every Wednesday from October to June, and you can go onto the MTNet EMinar site, EMinar webpage, and you can find previous ones, video links and presentations and upcoming ones. And I particularly want to advertise our last EMinar, which is in 2 weeks, which is going to be an open mic. We've never done this before, and the idea is to have a webinar where everyone just talks about issues and problems in MT or any aspect of EM, and we'll have a Zoom meeting. And then we're going to start season 3 in early October, so we're particularly looking for titles and topics, so please send those to us. The final EMinar of the season next week is Kate Brand, on an Australian, talking about the wonderful work the Aussies are doing in lithospheric architecture and mineral systems. So please join us. It's a later time next week. But today we've got Christine Chesley on seamounts and slow slip and hydrates. Oh my, marine electromagnetic investigation of the Hikurangi Margin of New York. Very quickly. I was going to give you a CV, but I've forgotten to write it down there, Christine. You can tell us all about you. So I'll hand over to Christine now. Sorry about that.
Okay, no worries, Alan. Hold on a sec. Let me just share my screen. Yeah, hopefully you can all see this. So I am currently a postdoctoral scholar at Woods Hole Oceanographic Institution, and I finished up my PhD at the end of November of last year, and then I got on a boat to start collecting data for my postdoc. But I'm going to be talking today about some of the work that I did for my PhD. I'm specifically going to be focusing on this seamounts and slow slip story, and I'll probably spend a little bit of time on some of the other results that we're finding from this massive data set that we collected off the North Island of New Zealand. And I know that Vipka talked about some of the onshore data probably a month ago, but I missed that talk. So I'm sorry if any of this is a repeat, but it's probably always a good idea to see things more than once. Before I get too much further along, I do just want to acknowledge some of the instrumental contributors on this work, including Sam Renaif, Carrie Key, Dan Bassett, Jake Perez, Chris Armerding, and the entire science and ship crew of our #resist project, who made sure that we collected the best data that we possibly could. So just to give you a sense of where we're headed for today, here's an outline of this talk. I'll start by providing some relevant tectonic background information on the Hikurangi Margin and why it's such an interesting subduction zone for us to study. And then I'll mention this somewhat debate on the role of subducting topography in megathrust slip before spending the majority of this time talking about this seamount story at the northern Hikurangi Margin and what we've learned for how seamounts might be affecting shallow slow slip. I will touch on some of our results, like I said, from the central and southern parts of the Hikurangi Margin before getting to some conclusions. So diving right in, this map shows the Hikurangi Margin. It's the subduction zone located east of New Zealand's North Island, and it represents convergence between the downgoing Pacific plate and the overriding Australian plate. And the Pacific plate is a little unique in this area because it is thickened relative to normal oceanic lithosphere by the presence of the Hikurangi Plateau, which is a large igneous province. Because of block rotation in this forearc, the convergence rate does decrease from north to south along the margin until by the time you get to the South Island of New Zealand, relative plate motion is entirely accommodated by strike slip faulting instead of by subduction. Now, something that has made this subduction zone such an interesting place to study subduction dynamics is that within a relatively small geographic area, there are several properties that vary along the strike of this margin. So one of the most important of those is this variation in interseismic coupling, which decreases from north to south along the margin. And you can see that denoted here by the coupling coefficient, where reds are higher coupling coefficients in the south and blues are lower coupling coefficients in the north. So coupling, basically, this coupling coefficient tells us how much of that relative plate convergence rate is being accommodated by creep as compared to plate locking. So in the south, we see more strongly locked plate interface, and that suggests that a stronger stresses can accumulate and potentially get released in more destructive earthquakes. Now, the southern part of this island hasn't actually seen a large magnitude greater than 8 subduction zone earthquake in historic times, but there is evidence for such large events in the geological past. Something that's very closely related to the variation in interseismic coupling is the variation in the occurrence of slow slip events, where there are shallower and more frequent slow slip events occurring in the northern part of the margin than in the south. So for those of you who aren't familiar with the term, a slow slip event is essentially just an earthquake that happens in slow motion. So slip in these events occurs over the course of maybe days or weeks or months, as compared with typical earthquakes where slip happens within seconds. So even though the same area of the plate is moving, because it's happening over such a long duration of time, you're not going to feel the ground shaking underneath you in these slow slip events. And you can see in purple here the contours of cumulative slip since 2002. It is thought by some that these slow slip events are related to the availability of fluids. And so that kind of gives you an indication why electromagnetic methods might be a perfect technique to use to study this problem further. I'm going to come back to this particular slow slip event that occurred in 2014 off the coast of Gisborne in the northern part of New Zealand, because it is sort of an infamous or famous slow slip event where slip was recorded almost all the way up to the trench. So these lines here are the slab depth contours, and these colored shadings are the slip patches. And you can see slip is going almost all the way to 0. So just keep this in the back of your head because I'll be referencing it later. The last along strike variation that I'll mention is this noticeable change in the exposure of seafloor topography, with rougher seafloor being evident in the northern part of the Hikurangi Margin as compared to the southern part of the margin. So I'm also going to be coming back to this seismic reflection profile from the northern part of the margin because it is co-located with one of our electromagnetic profiles. And in it, you can see this well-exposed seamount on the incoming plate. And then if you look at the forearc, there's this feature that's generally interpreted to be a subducting seamount as well. Now, there are probably seamounts in the southern part of the margin as well, because all of this lithosphere is part of the Hikurangi Plateau, but the southern part is very heavily sedimented. So if there are any seamounts down there, they're likely buried by that thick package of sediment. So these are the important along strike variations at the Hikurangi Margin. And we really don't know what causes the change in interseismic coupling or the occurrence of slow slip events. And I don't have like the final explanation for all of that today, but I do hope to convince you in what I'm going to show that seamounts are playing some role in those variations. And when I say seamount or subducting topography today, I'm going to mean any seafloor feature that rises above the seafloor, regardless of its size. And there's really sort of two camps of thought here in telling us what we think about how these seamounts and subducting topography should be affecting megathrust slip. So the first one was popularized by this paper by Mark Close, and it suggests that seamounts should act as frictional asperities that subduct against large frictional resistance and thus increase the stress buildup and promote large earthquakes. In this other body of thought popularized by Wong and Bilek, these seamounts should instead promote the conditions that are going to favor smaller earthquakes and aseismic creep. And they do so by generating these complex fracture networks in the upper plate as they subduct. And these fracture planes are going to fail randomly and thus inhibit large earthquakes from occurring. And I do just want to point out that although these are conceptual models, they paint the seamount as a very homogeneous looking structure. And I will show today that we probably need to be considering the heterogeneity that is present internally to the seamount when we talk about how it's affecting megathrust slip. So there is, real life evidence that seems to support both of these bodies of thought, which is why they're still proposed and cited today. In this example from Kyriakopoulos and Newman, this is a study done at Costa Rica in which you can see an area of strong locking shown in red here. And this is where there's evidence for a subducting seamount. So it seems like the seamount is actually causing a lot of plate coupling here. On the other hand, in a study by Satish Singh and others, Satish Singh and others, they use deep penetrating seismic reflection data to show that there is this seamount located in a seismic gap, which I've circled here because there's no beach balls, so no seismicity in this area directly above where the seamount is. So I will say that it seems like more and more evidence is coming out in support of this second idea on how seamounts should be affecting megathrust slip. But it's been really hard to study these things because seamounts that are subducted are usually too deep into the subduction zone to image them very well. So we've generally had to rely on sorts of analog models and seismic reflection images of seamounts that are just beginning to subduct. So for example, in the central Hikurangi margin, we have a really nice seamount that is just at the trenchward-most part of the subduction zone, really. And you can see the faults that it's forming on the seafloor as it subducts. And you can also see how it's starting to fracture the upper plate. But this is the seismic reflection image from the northern part of the profile that I showed earlier. And without any interpretations drawn here, I think it's really hard to say that there is a seamount subducting, and even harder to see any of these fracture networks that it is purportedly forming. So I'll put the interpretations back up. But the question becomes, how can we image these seamounts at depth and the fracture networks that they're supposed to be forming in the upper plate? And it turns out that EM is actually a pretty good technique to use to try to address that problem. You've probably all seen some version of this figure before, but I just want to drive home a key point here, which is that if we focus on oceanic crust, we can see that its resistivity is predominantly controlled by its porosity. And that's because non-porous oceanic crust is so much more resistive than conductive seawater. And the same is true of marine sediments. So that fact allows us to infer the porosity of oceanic crust and seafloor sediments from knowledge of its resistivity, and that's going to be very useful here. I guess if you've seen like Steve Constable's talks or some other of the marine talks, then you probably are a little familiar with the marine MT and CSEM method, but I'll just remind you of it here. So the key difference, I think, one of the key differences between trying to do marine magnetotelluric studies versus land studies is that this magnetotelluric source current has to travel through several kilometers of conductive seawater in the marine setting. And so that means that the high frequency content is going to be attenuated below the noise floor of our seafloor receivers. And that's going to make this method more useful for when you're trying to study deeper into the lithosphere and the asthenosphere, which is why if we want to study the shallow lithospheric structure on the seafloor, we need to supplement marine MT with marine controlled source electromagnetic methods, or CSEM. And in this case, we're going to be towing a transmitter near our seafloor receivers and generating an alternating current, which of course is going to create primary and secondary electric and magnetic fields. And so this method is going to help us get at that shallow lithospheric resistivity structure. I also just like showing this video of what it looks like to deploy one of our receivers over the side of a ship. If you've never gone on a cruise before, then this might be your impetus to start thinking about going on these cruises. So these receivers have these electric field dipoles, which are the long blue arms, and our induction coil magnetometers, which are the little white things sticking out. We also attach a concrete slab to the base of this receiver, or else it would not get down to the seafloor because it is buoyant. And then when we want to get our data back, we just send a particular frequency through the water column, which triggers a release from that concrete slab. And then our data and the receiver can float back to the surface of the sea, and we can pick it up, hopefully. Okay, I also just want to show you this first CSEM image of a subduction zone. So this is the Middle America Trench offshore Nicaragua, and this was a study done by Sam Renaif and others. And for today, all of today, blues are resistive and reds are conductive. So this is showing us resistivity as a function of depth and distance from the Middle America Trench. Now, if we look at the abyssal plain here, we can see that the resistivity structure is generally 1D. I mean, it's kind of just increasing as a function of depth from the very conductive sediments near the surface, and it's getting more and more resistive as we go into the crust and the uppermost mantle and pore spaces close, and of course composition changes as well. But as this plate is approaching the trench, we start to see these higher conductivity tongues of material peeking into the oceanic crust. And they're basically occurring in the same location where you see outer-rise bending faults evident in the seafloor bathymetry. So this was really the first study in a very compelling case that showed how these outer-rise bending faults are acting as fluid pathways to hydrate the oceanic crust before it gets subducted back into the trench. Additionally, if you look at what's happening underneath the forearc, you'll see this high conductivity channel that's being subducted with the rest of the plate. And this is what we would call a subducting sediment channel. And it's been found at other non-accreting margins as well, which the Middle America Trench is an example of a non-accreting margin. Okay, but back to the Hikurangi margin. So our study, the Hikurangi Trench Regional Electromagnetic Survey to image the subduction thrust, was work that we carried out about 3.5 years ago at this point, from December of 2018 to February 2019. And this was the largest to date, I believe, offshore deployment of OBEMs, our ocean bottom electromagnetometers, to collect CSEM and MT data. So we collected both types of data along these 3 trench crossing profiles and 1 trench parallel profile shown in orange. And the great thing about the trench crossing profiles is that they were co-located with multi-channel seismic reflection lines. So that allows us to do things like joint interpretation and possibly even joint inversion. And then we also left out this grid of 42 receivers shown as these purple squares for about a month in order to collect long period 3D MT data to get a better sense of what the deeper structure of this margin looks like. In addition to all of this offshore data that we collected, GNS Science New Zealand has collected a lot of onshore land MT data, and this map is probably not the most recent up-to-date one, but at the time that I created it, it did have all of the land MT sites shown in green. So this is a massive amphibious electromagnetic array that can be used to get a really good sense of the resistivity structure of New Zealand and of this margin. So far, I have processed, inverted, and analyzed the data from the 3 trench crossing profiles. So I'm going to show you what the final models from all 3 of those look like in the same slide here. This is resistivity, again, as a function of depth and now distance from the Hikurangi trench. The trench is denoted by this dashed line. And as another reminder, the blues are more resistive, the reds are more conductive. I'll just mention that in doing isotropic inversions initially of these lines, it was obvious that the sediments required some sort of anisotropy. And so these are all anisotropic inversions. They're transverse isotropies, so it's really vertical anisotropy here, and I'm showing the vertical component of resistivity. Looking at all 3 of these profiles together, I think it's very shocking to see how different each of these looks, even though they all come from the same subduction zone. And you can see as we go from south to north, just the increasing amount of heterogeneity that is present within the resistivities of these lines. So I'm going to walk us through each of these lines and spend the most time, like I said, on the northern profile here. So let's start with that. And this, information on this line is published in a paper in Nature that came out last year. So if you want to learn more about what was happening here, you can check that paper out. Basically, what this zoom-in map shows are some of the observations that have been conducted in this area. This is probably the most heavily studied part of the margin, so this map is by no means comprehensive, but some key features to note here are seafloor receivers shown as these gray squares. There are also 4 IODP drill cores taken along this profile shown in red dots here. And evidence of fluid seeps is shown by these cyan colored squares. The orange outlines are the slip contours from that 2014 slow slip event that I mentioned earlier. And the white stars are repeating earthquakes associated with that particular slow slip event. This blue star out here is the approximate epicenter of the 1947 tsunami earthquake. And if you look on the incoming plate, there's this feature called Turanganui Knoll, which is the seamount for the incoming plate that was seen in the seismic reflection data that I showed a bit earlier. And then there's also this white outline here, which represents a magnetic anomaly inversion of that subducting seamount. I want to show you some of our data from these 2 sites, one of them located on the Seamount Turanganui Knoll, and one of them in the Forearc. So just to give you a sense of what our CSEM data quality looked like for this study, here are the stacked amplitude and phases from the 3/4 Hertz frequency for that Seamount Turanganui Knoll in blue, and for a site on the Forearc shown in green. So I'm not going to spend too much time talking about what each of these really means in depth. If you want to know more about that, you can ask questions later. This is on the x-axis, the transmitter receiver offset, and the top plot is the amplitude and the bottom plot is the phase. And we had really clean low noise data, as you can see from these images here. And you can also see that there's clear structural differences between the data that we collected on the Seamount and on the Forearc, where the Seamount, we have really long offsets, and the Forearc, the amplitudes and phases just decay very rapidly. So that indicates something to us already, which you probably are aware of if you use this data a lot. Also, it's always important to look at your data before you try to model it, and very important to try to assess the dimensionality of your MT data before you decide if a 2D model or a 3D inversion algorithm is necessary. So because I'm inverting all of these data with Mare 2DM, that is a 2D code, and we can't be giving 3D data to 2D codes. So just as a reminder of like the key of what is 1D, 2D, and most likely 3D, this is up here from Sammer's thesis. And what we can see is that many of the longer period data is 3D. And also a lot of the incoming plate data is 3D. So I did not use any of the MT data from the incoming plate in this inversion. And I was very careful in choosing what data to use to invert for the Forearc. But that was totally okay because we're mostly interested in shallow structure anyway, and we have CSEM data for the entire profile. So here again is what our final inversion model looks like. It is probably looking slightly different from what I showed earlier. That's just because I've increased the limits of the color scale, but it is the same model. And I like to show, when I have time to make these kinds of maps, the resistivity model with some of the seafloor bathymetry, because you can start to try to find where features in the resistivity might be connecting up to some of the features that you see on the seafloor. So for example, there's this arm of more conductive material that seems to be reaching up to one of these seafloor ridges, and that might suggest where we have a fluid pathway. Oh, so I just, looking at that image, there is a lot to take in at once. So I do want to break it down into the incoming plate and Forearc and just talk about each of those in turn. Starting with the incoming plate resistivity. Here in this model, or in this profile, it's pretty much dominated by that Turanganui Knoll seamount and also by the Hikurangi Trough. So Turanganui Knoll, we do call it a seamount, but it's actually more morphologically similar to a geo, which is a flat top seamount. And seamounts become geos when they rise to the surface of sea level or above and are eroded by wave action and then later thermally subside. Now, it is interesting that it's not flat topped anymore, and that's probably because of later stage volcanism that emplaced, for example, these little cones. We did have a great opportunity here to really extensively characterize the electrical structure of this seamount. And so this is what we found this seamount included. It includes this very resistive core of material, which I've outlined and called R1P. Now, because of its high resistivity, we know that it's going to have a low porosity. And based on what we think we know about how seamounts form, that suggests that R1P is likely an intrusive core made up of gabbroic material. Cutting into that resistive core is this conductive fault C2P, which actually coincides with a seismically imaged normal fault. Additionally, there are heat flow data in this region shown here as these red dots. The background heat flow is shown as this dashed line and one standard deviation away from the mean as a solid line. And what is really cool to see is that the heat flow values decrease upon approaching this fault, which suggests that the fault is a conduit for fluids from hydrothermal recharge. There's also some heat flow data that seems to go up above one of the cones here, and that is suggesting that this entire seamount is actively participating in hydrothermal recharge and discharge. Sitting on top of this resistive core is this conductive matrix of material C1P. Again, because it's conductive, we know that it's going to have a higher porosity than the core. And based on what we know about how seamounts form, we would interpret C1P to be some sort of matrix of volcaniclastic material, extrusives, and probably some altered hydrothermal minerals as well. And then finally on Hikurangi Knoll is this resistive cap R2P. My interpretation for how R2P formed, because it is resistive and therefore lower in porosity than the stuff that's sitting underneath it, is that as this seamount was building and building and building and finally breached the surface of sea level, that basaltic material that was creating it was no longer coming into contact with cold seawater. And so it was allowed to cool slowly in a subaerial environment and thus maintain that low porosity. Moving into the Hikurangi Trough. In the northern part of the Hikurangi margin, we can see here, the trough has about 1.5 kilometers of conductive sediments that are siliciclastic and pelagic in origin. And then there is this unit called Seismic Unit 8, which is shown in blue. And this unit is essentially cones of volcanic material. So it's material that is, volcanic igneous in origin, but it's not as large of a feature as these seamounts that you see on the seafloor. And it's interesting to note that the resistivity within these little cones is higher than the resistivity of the sediments, but it's actually lower than R1P and R2P. So that suggests that these cones were formed extrusively rather than intrusively or subaerially. Now below the base of Seismic Unit 8 is this subhorizontal resistor that seems like it might be coming off R2P. And my interpretation for how R2.5P formed is that as R2P was forming subaerially, some of that basaltic material flowed down the flanks of Hikurangi Knoll and back onto the seafloor. And that's why we have this subhorizontal resistor. So that would mean that C3P, which is underneath R2.5P, is likely some sediments that got buried by that flow. Okay, as I mentioned before, we can use our resistivity data to infer something about porosity. And that typically we will in our field do that with Archie's law. Archie's law has its drawbacks, but it's pretty useful for at least trying to determine relative porosities, even if there are some issues with absolute porosities. So keeping that in mind, but knowing that our bulk resistivity is essentially constrained by the EM data. So that's rho in this equation. And then we have a pretty good sense of what the fluid resistivity should be because our transmitter that we tow has a CTD on it. So it's measuring the conductivity temperature and depth of, it's measuring conductivity temperature and depth. And so we can get a pretty good sense of the fluid resistivity from knowledge of that and knowledge of the geotherm, which we can take from the IODP drill cores. The cementation factor M is always the trickiest part of this equation. And for this study, or for the images that I'm going to show, I used a value of M, which is taken from work done at the southern part of the Hikurangi margin. So converting that resistivity into porosity space, here is what the porosity looks like. You'll notice, of course, the Hikurangi trough sediments have a high porosity. That's because they haven't compacted very much, so they still have a lot of their pore space. But Additionally, Hikurangi Knoll is actually quite porous for oceanic crust. And to just do a comparison here, these are some drill cores into oceanic crust near the Mid-Atlantic Ridge and the East Pacific Rise. And you can see that the porosity of these cores into the crust is decreasing down to 2% in the upper 1 kilometer of this core. But I've estimated that Hikurangi Knoll is about 9 to 13% porous in the upper 3 kilometers of that seamount. So that's way more porous than average oceanic crust. Doing a slightly more direct comparison in terms of methodology, I estimated what the porosity difference would be for the abyssal hill, the abyssal plain in that Middle America Trench study. So before the outer ice bending faults. And I estimate that Hikurangi Knoll will carry around 3 to 5 times more water with it to the subduction zone than that unfaulted normal oceanic crust. So that's a lot of water. And I think this result was really exciting because I don't think people have generally considered how much water these seamounts are locally transporting with them to subduction zones. And that water is going to influence the different processes that occur at subduction zones, like potentially shallow slow slip. So let's take a look again at the forearc. I think if you sit really far away from this figure and you squint your eyes, it does look like what we would expect a forearc to look like. You know, it's got conductive sediments in the shallow part here, and also the slab is dipping and resistive, which is what we would expect as well. But overall, this is a very heterogeneous Forearc resistivity structure, much more so than any of the other profiles that we've looked at today. So I'm again going to step through some of the key features in this Forearc model, starting with C4F, which I would argue is likely a small package of subducting sediment, both because of its higher conductivity and the fact that it is occurring sort of at the edge of the décollement, which is just a fancy-ish word for the plate interface. There are also 3 main conductors that are embedded in a more resistive background here. And some of these conductors are bounded by active thrust faults like the top of this one here. And based on the prevalence of fluid seeps in this region and the way that some of these conductors are following these faults, it's possible that we are seeing some sort of fluid pathways being imaged here. It's also very possible that some of these conductors are sediment underplating. And I've plotted the projection of the 1947 tsunami earthquake on this profile so you can see just how close it plots to this conductor C3F. So when we call an earthquake a tsunami earthquake, we mean that the earthquake generated a tsunami that's larger than expected based on the magnitude of the earthquake. And it has been speculated that low rigidity material in an accretionary wedge, like potentially underplated sediments, could contribute to tsunami generation. So I think that is a pretty plausible explanation for what C3F might be. And it's also possible that C1 and C2F are underplated sediments as well, but I would argue for a different interpretation related to this feature on the subducting slab, R1F. So R1F, I would argue, is the resistive core of a subducting seamount, similar to R1P of Hikurangi Knoll on the incoming plate. And what gives us confidence that that is likely what this feature is that it sort of overlaps with the area that the seismic reflection and the magnetic inversions show have a subducting seamount as well. And there's this more recent study from Ryuta Arai-san in which he used VP data to show that there's this high velocity anomaly which happens to be sort of centered in the same area as R1F and have a similar peaked shape. So that gives us even more confidence that this R1F feature is likely the core of a subducting seamount. So based on the proximity of R1F to C1 and C2F, I would argue that these conductors are likely related to damage caused by this subducting seamount and the enhancement of porosity caused by that damage. And I should also mention that they could be related to fluid transfer from this high reflectivity zone, which has been interpreted to be sediments, fluid-rich sediments, entrained at the toe of the subducting seamount. And you can see that there is a change from a compressional regime to an extensional regime that happens around where C1F is. So it's possible that that extensional regime or that extension is driving some of these fluids upwards into C1F. But I just want to add one more layer to this. So this is that same seismic reflection image that we've seen a couple of times now. In this particular study by Heather Shaddix and Susan Schwartz, the authors were interested in relocating some of the seismicity from that 2014 famous slow slip event. And in particular, they wanted to look at this type of earthquakes called burst type repeating earthquakes. And those have been associated with fluid migration. So I'm going to show you where the relocated events plot relative to our resistivity model. So here they are in the white circles and white stars. And sort of amazingly, much of the seismicity is plotting in and around this C2F conductor. So we think this is likely the closest thing to in situ evidence that is directly linking the effects of damage from a subducting topography to the generation of a fracture network and the transfer of fluids into that fracture network that is somehow linked to shallow slow slipping at the Hikurangi margin. So I'm going to move on to the other profiles now, starting with the central profile. And this profile was designed so that it would be in the area that sort of transitions from strong plate locking in the south to aseismic slipping in the north. You can see that the forearc of this margin is very large in the central part. So most of this profile is actually forearc and not incoming plate. So here again is what the resistivity model looks like. And compared to the northern profile, we see a much simpler incoming plate resistivity structure and forearc resistivity structure. And we don't see any evidence for large seamounts in this profile. It's helpful to look at this profile, and I think any EM profiles with the multi-channel seismic reflection overlays. So Andrew Gase has been very gracious in allowing me to show some of this ahead of publication of his interpretations and his work here. So I've also included the 2.7 and 10 ohmmeter resistivity contours in black. And then Andrew's picks for the top of the Hikurangi plateau are shown as these red dots, and the bottom simulating reflector I'll show in a second in blue. So there are several pockets of high resistivity in the shallow part of this forearc, and they're occurring, above the bottom simulating reflector. And these are most likely showing us where there is free gas or gas hydrates. We kind of know from other studies that this is a very gaseous margin. So it makes sense that a lot of these high resistivity anomalies that we're seeing in the forearc are related to gas or gas hydrate. There's also this upward dip in the resistivity that is happening closer to the landward side of this profile. And interestingly enough, there is an upward dip in the reflectivity as well. So it turns out that this is actually not the plate doing something weird where it's dipping and suddenly up dipping. This is actually part of the upper plate. So it's the Mesozoic basement of the upper plate, not the subducting slab. And then again, we see these anomalous forearc conductors, which might be associated with damage from maybe smaller topography. So nothing as large as Turanganui Knoll size topography, but maybe smaller features, or it could be related to underplating sediment again. Interestingly, some of these conductors appear to be separated by thrust faults. So that might suggest that the thrust faults are separating differences in pre-existing geology. And then what's also very interesting is that there are these high reflectivity zones, which Andrew has outlined here. And those seem to be broken up by where we see these conductors. So we're still thinking about what this means, but it's possible that we are getting indications of heterogeneous fluid distribution at the plate interface in this part of the margin. Okay, the final profile comes from the southern part of the Hikurangi margin. And already from looking at the bathymetry, you can see there's really no exposure of any topography. It's a very smooth seafloor here. And that is because the sediments in this part of the margin are just so thick on the incoming plate. So here again is that resistivity model. And compared to the northern and central profiles, this is a much simpler profile. And if we use the 10 ohm-meter contour as the approximate base of the sediments, then we see that there are around 4 to 6 kilometers of sediment on the incoming plate here. Additionally, it's, I think, beneficial to see that some of our resistivity interpretations are matching up with the seismic reflection. So the seismic reflection data here hasn't been depth migrated yet. So I just tried to do a quick and dirty migration of some of the interpretations from the seismic data. And this 10 ohm-meter contour is approximately matching up with the top of the Hikurangi plateau. There are some anomalous resistors in the forearc in this profile as well, R1 and R12. And again, these are likely indicating where we have some free gas or gas hydrate. And I've put in the approximate base of the gas hydrate stability, so you can see that, yes, those resistors are occurring around or above the base of gas hydrate stability. Okay, I converted this profile, well, I converted the resistivity to porosity for this profile as well. And, you know, this porosity model looks very boring to me, but that's because we're really only seeing the first order trend here, which is the decrease of porosity with depth as those pore spaces close from compaction and overburden. So I wanted to see if there was any more information that we could squeeze out of this porosity data. So I tried removing the dominant 1D compaction trend from this section of the incoming plate sediments to see what might be left behind. So this is a porosity anomaly model. The purples here indicate that the incoming plate sediments are more porous than what would be expected from vertical compaction alone. And the orangish brownish color indicates that the sediments are less porous than vertical compaction would predict. And the thing that sticks out here is this increasing negative trend in the porosity, in the negative porosity anomaly as this incoming plate sediment is approaching the trench. So that suggests that there is some force in addition to compaction that is causing the porosity to decrease as you get closer and closer to the trench. And that is almost certainly the force of lateral compression. And so this is suggesting to us that we are seeing through this EM data the early stages of protothrust zone development, which is important because it indicates where you might start to see the seaward translation of the trench. Okay, so to wrap things up, I'll just remind us that today we've seen the first electromagnetic image of subducting topography, and we've learned that these seamounts can carry with them underappreciated amounts of water to the subduction zone, and that water is likely influencing processes that happen like shallow slow slip. We've also seen that the Hikurangi margin has a very heterogeneous electrical resistivity structure as you go from south to north, and that is likely related to the exposure of the seafloor topography. So thank you all for listening, and I hope to take any questions that you have.
Thank you. That was absolutely brilliant, Christine. Please, everybody, send your questions in Q&A. That was a huge overview, and I've got a load of questions written here. But I'm going to let other people, while some questions roll in, just if I can talk to you a little bit about resolution, because I was looking at, as you were presenting the work, it seemed to me like if we're looking now, some of those resistors, like in the bottom image, R1, R2, and then in the middle image, R4, R7, R8, they seem to predominantly occur in between stations. And I'm just wondering whether there's some sort of inversion artifact. I mean, I'm much more familiar with land MT, and if I saw that in land MT image, I'd begin to think there was distortion in the data that was being accommodated by putting resistors off to the side. So forgive me if I'm getting this totally wrong on the ocean floor and with CS EM.
Oh yeah, no worries. It's a very fair question, and one that we had as well. So it does, I have done quite a few sensitivity studies, and these resistors are required by the data, perhaps not in this particular shape, but you can also actually in the CSEM data see the effects of some of these resistors because the amplitudes will be increased if you look at the offset where these resistors occur. So yeah, those resistors aren't just artifacts that are happening in between the stations, although it would be really helpful if we had good data from those missing receivers.
I see.
Yeah.
Yeah, that's a bit of a worry. Yeah, the other thing that in land-based magnetotellurics, we're not very sensitive to the top of a resistive zone. And so some of the interfaces you've drawn there in an MT image, I would begin to suspect that we don't have sufficient resolution in the MT data, but you're using a control source EM, so you're getting both toroidal and poloidal current flows. And so you probably have much better sensitivity to the bottom of a conductor, the top of a resistor.
Yeah, so that's you've kind of said it pretty well about how it's really effective and helpful to have these complementary sensitivities when you're doing a joint inversion with CSEM and MT. So these shallow resistors are certainly constrained by the CSEM data, not so much the MT data. And then when we're starting to see the tops of these resistors at depth, I would say that's most likely because the MT is able to sense the bottom of the conductive sediment package and just giving us some indication as where that sediment is ending.
Yeah, and another one, so nobody else seems to have questions for you. So I'm sorry.
I confused everyone, I'm sorry.
Yeah, the conversion to porosity. I just wonder whether it's valid to use the same M for different lithologies, whether you don't need to have a varying M depending on the lithology. And whether, in fact, if you took that last image where you were arguing that there was lateral compression because there wasn't sufficient vertical compaction, I wonder whether you could do the opposite and say, what M would I need in my lithologies to give me a porosity that agreed with compaction theory?
Oh, okay. Yeah, so you do make a good point about the M depending on the lithology, and that's something that is just, you know, it's something that we need to do more work on in lab data, to take these cores that we've got and then try to figure out what the M's are for the different lithologies in the cores. For this last image that I was showing here that you mentioned, what I actually did, and I don't know, this is not going to be a good one. So what I actually did or attempted to do was to take into consideration how the lithology is changing when I built a compaction model. So it wasn't a simple like one compaction model that worked. I don't know how to, I'm not explaining this well, but essentially I made a compaction model that was based on where the boundaries for each of these units was before I subtracted that compaction model off. I don't know if that makes, if what I'm saying makes sense. I'm sure I have a figure somewhere to explain this. Let me see. I might not have included it though. Yep, I took it out. Yeah, I took it out. Sorry about that, but I try to take into consideration what you're saying in order to not have that kind of lithological artifact in the porosity anomaly.
Yeah. Okay. Well, nobody else seems to be giving questions, so I think perhaps we should thank you again for absolutely wonderful work that you've done, and this overview. It's amazing. This could have been a 3-hour talk. You know, there's so much packed into it. Absolutely brilliant. So thanks very much again. And this recording will be on live in a couple of hours. And perhaps if Christine agrees, I can put your PowerPoint, your presentation up as well.
Yes, I will send.
And then anyone could send questions to Christine. So thanks everybody, and I'll see you next week. Well, I won't. Yeah, it's late. I won't see you next week because the EMinar's at a time when I'll be on an aeroplane actually. So it'll be hosted by Stefan Thiel. So bye everyone. Thanks for attending. Bye, Christine.
Thanks, Alan. Bye.